So let's get some properties of logarithms here. So one of the properties is if you have a logarithm with any base and you're taking a logarithm of 1. So let's think about this for a second. We have a base of a. We don't know what our exponent is, and we're saying we get out a value of 1. Well, to have a base and an exponent and getting 1 out, that means our exponent has to be 0. So the property goes that a logarithm with any base of 1 is always going to equal 0. We would always need that exponent of 0 in order to get 1 out. So that's one property that's helpful for whenever you're taking a logarithm of 1. This one here, the logarithm of base a of a. So this one, we have a base of a, we're solving for our exponent, and we're saying the value that comes out is a. So if the base and value match, what we would need for our exponent is a value of 1. So if you're taking a logarithm and the base and value of that logarithm match up, you're always going to have an output of 1 because that would be the exponent that we need. Then our last kind of special property here, so if you have a logarithm with base a of a to the power of x, so let's see how this kind of works out. We have base a, we're trying to figure out what that exponent would be, and we're saying that equals a to the x. We're saying what exponent do we need on a to get a to the x? Well, that exponent of x is exactly what we need. So if you're taking a logarithm where the base of the logarithm is matching the base of an exponential expression inside the logarithm, all that's going to come out of it is that exponent from that value. So those are some special properties. Let's get to some rules that help us condense and expand our logarithmic expressions. So one of them is going to be, I'm going to throw some parentheses in here. So the product property. If you're taking a logarithm base a of m times n. So m times n is the value of our logarithm. What we can do is expand this to be addition between the two. So it's the fact that multiplication inside the logarithm can be separated to addition outside the logarithm. So logarithm of base a of m times n is the same as log base a of m plus log base a of n. So we can separate it out. So going in that direction is called expanding. We could go in the other direction too. So if you have two logarithms of the same base adding together, what you can do is combine that or condense it into a single logarithm where you're multiplying those two values. What is key is that it has to be the same base for the logarithms that you're adding together. So that's where we can either expand to addition or condense to multiplication. The quotient property is if we're taking a logarithm of base a of m divided by n, what we can do is if we have division in the logarithm, that can translate to subtraction between two logarithms. So this one order matters. It needs to go the value in the numerator minus value in the denominator. So logarithm base a of m divided by n is the same as log base a of m minus log base a of n. And again, we can go in either direction. We can either expand to subtraction or condense to division. It just depends on what we need to do when we get to solving logarithmic equations. Typically, it's this condensing direction that can be helpful, so changing things into just a single logarithm rather than multiple separate logarithms. But really, we could go in either direction. And then our last piece here, the exponent property. So if we have log base a of x to the power of n, what we can do is take that exponent on x and bring it out front. So exponent comes out front, so what we have is n times logarithm base a of x. And then x no longer has, or it has an exponent of 1 now by moving that piece out front. Some of the other lecture videos, or you can find them on YouTube, there's proofs of all of these. I'm not going to worry too much about proving them, but if you're wondering why these work, it really ties to our exponent rules. So there are reasons for all of these properties. It isn't just magic, but how we're going to use it can feel a bit like magic sometimes. All right. So with those different rules, let's go ahead and simplify some expressions, and then we'll look at expanding and condensing to kind of see how it all comes together. In this section, I'm showing lots of examples because it's a new notation, it's kind of a new concept, and just the more you can see, hopefully that can help make it click for you. Okay. So this first example, we have a logarithm with base 2 of 2 to the 5th. So this is a case where the base of the logarithm is matching the base of this exponential expression inside the logarithm. So when those match up, it's almost like this cancellation occurs, and all we're going to be left with is that exponent of 5. Again, it's like I'm asking, okay, that base of 2, what exponent do I need to get to the 5th? Well, I need an exponent of 5. So that's what we solve for here. We would need that exponent of 5 to kind of answer this question for us. For this one, we have 4 raised to the log base 4 of 16. And I'm realizing I didn't put this as one of the properties up above there. So let's add this in real quick. So in this case, we have the base of an exponential form matches the base of a logarithm in the exponent. All right, let's write this out. If we have base a raised to the power of log base a of x, what ends up happening is the base of the exponent kind of cancels with that base of the logarithm, kind of like we saw with that previous example. Basically, all we're going to end up with is x at the end. So this 4 raised to the log base 4 of 16, those kind of cancel out, and all we're going to be left with is that value of 16. We could have also actually simplified this one pretty nicely. So if I kept that base of 4, log base 4 of 16, so 4 to what exponent would give us 16? Well, we would need a 2. And 4 squared would be 16. So we could have evaluated the logarithm up there since it wasn't too bad. All right, this one uses that property nicely. So we have e raised to the natural log. So this is a case where the base of the exponent matches the base of the logarithm. So that's just going to cancel out and leave us with that x over 6. So that would be where we end up with that one. Log of 10x squared minus 2. So we have a logarithm base 10. And then for our value, we have base 10 of x squared minus 2. This is another case where the base of the logarithm cancels out with the base of the exponent. So all we'll be left with here is x squared minus 2. All right. Down here, let's see. Let's go ahead and condense this. So I have a logarithm base 8 of 16 minus logarithm base 8 of 2. What we can do is condense this into division. So using our quotient property, if we have subtraction between 2 logarithms with the same base, we can condense it to 1 logarithm of that same base. And then what we do is we do division. So this would be 16 divided by 2. So we end up with log base 8 of 16 divided by 2. Log base 8 of 16 divided by 2 is 8. And when the base matches the value, that means we just need an exponent of 1. So that's all going to simplify to 1. Log base 8 of 8 is equal to 1 for that exponent that we would need. All right. How about log base 6 of 9 plus log base 6 of 4? So this is addition between 2 logarithms. what we can do is condense this using the product property. So condense it to log base 6 of, and then it'll be multiplication, so we'll have 9 times 4. So we're taking log base 6 of 36. And what we're asking ourselves here is, okay, 6 raised to what power would give us 36? Well, we would want 6 squared. So we would need an exponent of 2. So our final answer is going to be that exponent of 2. All right, and then log base 2 of 8 cubed. There's a few different ways we can go about this one. Let's use that exponent property. So we have log base 2 of 8 cubed. What I'm going to do is take that exponent of 3 and move it out front. So that would be 3 times log base 2 of 8. And now I have something that I can simplify nicely, because what I would be asking myself is 2 raised to what power would give us 8? Well, we would need a power of 3. So we want an exponent of 3. So we end up with 3 times, and then that log base 2 of 8 we can replace with that exponent that we would need of 3. And then 3 times 3 is 9. Okay, so there's some ways of simplifying expressions. Now let's look at expanding expressions. So I have log base 2 of x cubed over y squared. So expanding, so we have a single logarithm with division in it. So what we can do is separate it out using subtraction. So all I'll do is take log base 2 of that numerator, x cubed, and then I'm going to go minus log base 2 of the denominator, y squared. And then what I'm going to do is I'm going to go one step further, because we have this x cubed and y squared. What I can do is bring those exponents out front. That'll expand this even more. So it would be log base 2 of x cubed is the same as 3 times log base 2 of x. And then minus log base 2 of y squared is the same as 2 times logarithm base 2 of y. And now that's all we can do with it. It's fully expanded in kind of its longest form. Sometimes during expansion, what we might find is we might find something that we can simplify. So that's a nice part of this process, is starting with something so condensed and maybe kind of confusing. During expansion, we might come across something like, oh, we can evaluate that logarithm without a calculator, and we might be able to simplify things. All right, natural log of w to the 4th times cube root of u. Let's talk about rational exponents real quick. I did it slightly in a previous example. So in a previous example, I talked about how 10 to the 1/2 is equal to the square root of 10. Those are the same thing, and the idea is that a square root is the same as having an exponent of 1 over 2. The rule goes that if we have x to the 1 over n, that is equal to the nth root of x. So basically the denominator of your exponent matches up with the level of root that you're taking. So what I'm going to do is, since we have the cube root of u, just because our exponential form can help us here with our logarithms, I'm going to change this to u to the 1/3. So the exponent is going to be 1/3 so that it matches up with that cube root. So I'm just going to rewrite this natural log of w to the 4th times u to the 1/3. Okay, so we have multiplication inside the logarithm. So what we can do is expand using addition. So I'm going to have natural log of w to the 4th plus natural log of u to the 1/3. Then, kind of like with that previous example, we can take those exponents and bring them out front. So natural log of w to the 4th is the same as 4 times natural log of w, and then plus 1/3 times natural log of u. And then that would be as far as we could go with that. So that's expanding, starting with typically a single expression and expanding it out. Condensing. So making it smaller, which as I was saying before, that's kind of the more typical case. So we have 2 times log base 9 of c plus log base 9 of a over 3. What I'm going to do is I'm just going to rewrite this. So 2 times log base 9 of c plus, instead of log base 9 of a over 3, I'm going to write this as 1/3 times log base 9 of a. Mostly because of what we just did in that previous example. Okay, so we have these numbers out front, and what we need to do is get those inside the logarithm. So what we're going to do is we're going to reverse that exponent property. So having a 2 out front multiplying is the same as bringing that n as an exponent of 2. And having the 1/3 multiplying outside is the same as bringing it in as an exponent on a. So 2 times log base 9 of c is the same as log base 9 of c squared. And then we have plus 1/3 log base 9 of a is the same as log base 9 of a with a power of 1/3. All right, so now I have these 2 logarithms adding together. So what we can do is condense this with multiplication. So we can combine this into a single logarithm, so log base 9 of, and then we'll have c squared times a to the 1/3, which is the same as the cube root of a. I'll just leave it like that. All right, our next one here. A few different ways to go about this. Let's just go piece by piece. Ooh, I'm gonna go ahead and like each of these is being divided by 3. You could factor out the 1/3 and then work from it there. It'll all be the same. Let's work with it piece by piece, just in case you come across an example where those denominators are different. But I am going to switch this to like 1/3 times log base 3 of x plus 1/3 log base 3 of y plus 1/3 log base 3 of z. And then what we could do is that 1/3 can come into each of those as an exponent. So log base 3 of x to the 1/3 plus log base 3 of y to the 1/3 plus log base 3 of z to the 1/3. And then what we have is addition between these. And we can actually combine these all at once. That wouldn't be true if it was subtraction. If it was subtraction, we would want to do that division step by step. But with multiplication, what you can imagine is our first step would be multiplying that x to the 1/3, y to the 1/3. And then we would just have that product times z to the 1/3, which is just the same as combining all of them. So let's go in one step of having log base 3 of x to the 1/3 times y to the 1/3 times z to the 1/3. And we could leave it like that. This is actually the same. I'm just going to write a few different ways. Log base 3 of, and this could be x times y times z all to the 1/3. That would be the same. You could also write it as log base 3 of the cube root of x times y times z. All of those are the same thing. We could have had them as 3 separated cube roots. There's a few different ways to go about it. If you did different steps like factoring out the 1/3, you should still get to that same answer in the end.